Hi everyone, I'm a PhD student at MIT, and I'm going to present my work on comparing similarity measures for neural networks and data sets. Alright, so we want to understand the brain, and for that we can study brains doing different cognitive tasks. We can record from different brain areas, and we can also build models to try to make sense of these recordings. And one important question is, how do we evaluate our models? And what do we actually mean by a good model? So one commonly used approach for recurrent neural networks is to look at the low-dimensional dynamics of the model and the data and try to see if we can find some similarities. But one limitation with this approach is that it really relies on the assumption of low dimensionality. And so it's not going to scale well to more naturalistic or complex behavior. Another approach that people have started to explore is try to use more quantitative similarity measures, but it also comes with its own set of problems and questions. So which specific measures should we choose? And there are many of them in the literature. And how can we interpret those scores and what can we learn from the scores? So I'm going to present you our attempt at applying these measures to recurrent neural networks. And then I will present you a new approach that we have started to explore, try to compare them and make sense of the scores. Okay. So how can we quantify similarity? So the problem is the following. We have some reference data set with some time-varying activity. Here in this cartoon, we have 6 conditions good for the 6 colors. And we also have a model data set that has the same shape. And we want to quantify how similar they are. Okay? So one very classical way to do it is to simply trying to predict our reference data sets in a linear way from our model data and measure how well we can predict it. Okay. Another commonly used approach is a method called centered kernel alignments, or CKA. And briefly, the idea is that we correlate the neural responses to pairs of conditions for both data sets to get what's called a dissimilarity matrix for X and Y, and then we can correlate these matrices together. And we're also considering a more recent metric proposed by Alex Williams, which tries to find the best orthogonal mapping between X and Y, and then correlates the de-aligned data sets. And here we're taking the score version of the metric so that we have something between 0 and 1. Alright, so to evaluate these metrics, we are considering 2 data sets from non-human primates, we call it from the PFC, for a simple contextual visual integration task. So it's a simple task where you have a color of dots and there is a contextual cue that indicates whether you have to pay attention to the color or the motion of the dots. Okay, so we can train some RNNs on this task. And we did that for 3 commonly used recurrent neural network architectures and 3 nonlinearities for each, just to have some diversity of architectures here. Alright, so I'm going to show you now the results of applying these metrics to these RNNs for the first data set. So here I'm going to plot the scores, where a score of 1 means perfect similarity for all the measures. Okay. So here are the different scores that we got, and maybe a first observation that we can make is that the measures give really different values for the scores. And also when we compare the scores to some baselines, for example, this baseline 2, the cross-condition average, it's not clear whether the models are better or not to this baseline. So for linear regression, they are better, for CK, they are worse, and for T angular, they're about the same. And we get also some similar results for the other data sets, where we found a lot of disagreements between the metrics. For example, here if we look at CKA, it seems that the LSTM models in orange are better than the other models. But it's not really clear that's the case if we look at the linear regression score. So what these results, or maybe negative results, really told us is that before we can say anything meaningful about the models, maybe we should try to compare the metrics and then understand the scores that they give. And so here I'm going to present you an approach to understand what drives the similarity scores, and also specifically if for a given metric, if it's possible to find a data set that can have really high scores without encoding the relevant aspects of the data set. All right, so here's what we're going to do. We're going to take some reference data set, which could be our brain data set, or here we're going to start with a simple 2D data set. That's on one side, and on the other side, we're going to start with just some random noise. Okay. And what we're going to do is to optimize the data points in Y, so in our random noise, so to maximize the score between Y and X. And hopefully we'll get something that looks more and more similar to our reference data. Yeah, so more specifically, we can do gradient descent on the score function to find and optimize Y to maximize score. And this is a general approach. It only requires differentiability of the score, but I'm going to show you the results for the three metrics that I presented at the beginning. All right, so let me show you what it looks like. So we have our reference data, and here we optimize random noise to maximize the linear regression score. And as you can see, we start with noise, and then we get something that looks like a reference. It's not exactly the same because you can have a linear mapping between the two. So one way to characterize this optimization dynamics is to look at the variance of each principal component of our reference data X captured by the iterates Y. And as you can see on the plot, we start with a low score of 0 on the left, and as we optimize Y, we get closer and closer to 1, and we start capturing PC1 and then PC2. We get something really different when we optimize for CKA. So it seems that when we optimize for CKA, there are kind of two phases. The first phase where you capture only PC1, and later when the score is getting really, really close to 1, you only start capturing PC2. And you can see that in the animation where it first kind of stretch out, and then you capture the curvature only later. And this can be very problematic if, for example, PC2 encodes some relevant aspects of the task. Here you could get really high scores without even caring about this. And for properties, you cannot directly get the shape right. Okay. So before moving to neural data, I wanted to make another point, which has already been emphasized, but it's an important point. And to make that point, I'm going to just embed our 2D data set into a 3D space and do exactly the same thing, so optimize similarity. And this is what we get when we optimize for the linear regression score. So as you can see, the score is perfect. It's a score of 1. But we don't get something that looks exactly like the reference data. And it's because for linear regression, we just care about being able to predict the reference data sets. And so outside of the predictive dimensions, the data is still just noise, because linear regression doesn't care about it. And so it's a bit like these visual illusions where it's only when you look at the really right angle that you really see the picture, and when you just look at other dimensions, just noise. And this doesn't happen for CKA or for this data, where it converges to something that has the same dimensionality as the reference data. All right, so let's move to neural data now. I'm going to plot the same plots as before. So on the y-axis is the variance of the X data set, so here the neural data sets for each principal component captured by the optimized data Y. Okay? So again, the score will start on the left with small scores, and as we optimize Y, we will get closer and closer to 1. And I'm also going to color the different curves with the log of the variance of each PC. So as you can see, when we optimize the score, we first capture the first principal components, and the lower variance principal components are captured later for higher scores, as we expect. For the other metrics, we get really different profiles. For CKA, the lower variance species are captured very late, so you need to get really close to 1. Whereas for prothesis angular, you kind of progressively capture the PCs as you get closer to 1. And we find same thing for the other data sets. So this is really showing some intrinsic differences between these metrics and how they kind of weight different principal components. This can be important because the low variance species can encode some relevant aspects of the task. So if for CKA we can get really high scores without capturing these species, then it can be really problematic. And we can look if this is a problem or not here. So first I'm going to show you the decoding accuracy for the different task variables, so the context, the response, or the color direction of the dots, as a function of the number of principal components included in the data. So let's focus on the context here, because the effect is more pronounced. So you can see for the Mente dataset, we need to include at least 5 first species before we can fully decode the context. And for the SQL dataset, we need even more principal components. We need at least 20 principal components before we can decode context. Okay. So now we can look at the same decoding accuracy, so for the same variables, but we are trying to decode now the task variables from the optimized data sets. So the x-axis will be the same as before, so the score, and we go from left to right as we optimize. And the y-axis here now is showing the decoding accuracy. So here for this Mente data set, it seems to be okay. As we optimize, we can decode better and better the task variables. So this looks good. For CKA, if we look at this context variable, for example, if we take a score 0.9, we cannot still fully decode the context. Whereas for COSYNE Angular, it seems that we can decode all the variables correctly. And this is even more extreme for this data set. So now, if we look again at the score of 0.9, you can see that for linear regression, we cannot fully decode the context. For CKA, we can decode the context as well as in just the random noise, random initial noise. But for COSYNE, as we get a score of 1, we can decode everything. So yeah, so this is really problematic because when someone tells you, okay, I got a score of 0.9, I don't know, it sounds good because when 1 is the perfect score, 0.9 sounds good, but here's showing that it really depends on the metric, and so we should really try to understand these metrics and what they care about before we can say anything meaningful about the scores. All right, so what I've shown you is our first attempt to apply metrics to models with data, and we found that maybe we should benchmark metrics before we can benchmark models. And we have presented you a general approach for benchmarking these metrics. So predictivity is dependent similarity, as illustrated here. We found also that the COSYNE Angular metrics seems to capture the lower variance species sooner than other metrics like linear regression and CKA. And for linear regression and CKA, we can find really high scores without encoding the relevant task variables. And with that,